Gold ore. Gold ore refers to a naturally occurring mineral or rock that contains a sufficient concentration of gold, making it economically viable for mining and extraction. Gold ore typically forms in a variety of geological environments and is often found in association with other minerals such as quartz, pyrite, and sulfides. Its appearance can vary significantly depending on the type of deposit, ranging from visible gold grains embedded in quartz veins to microscopic gold particles locked within sulfide minerals. Types of gold ore. Gold ore can be classified into several types based on its geological origin and mineral composition. These include lode gold deposits, found in veins or fissures within rock formations. These deposits are often associated with quartz and sulfide minerals. Lode gold deposits are typically mined underground and are one of the most common sources of gold. Placer deposits, formed by the weathering and erosion of gold-bearing rocks. Placer deposits are found in riverbeds, streambeds, and other alluvial environments. The gold in these deposits is often in the form of nuggets, flakes, or fine particles. Carlin-type deposits. These are sedimentary-hosted deposits where microscopic gold particles are disseminated within sedimentary rocks, often associated with arsenic and antimony minerals. Carlin-type deposits are especially common in Nevada, USA. Epithermal deposits. These form near the Earth's surface from hydrothermal fluids. Gold in epithermal deposits is often found with silver and other precious metals. Porphyry deposits, found in large, low-grade disseminated deposits associated with porphyritic igneous rocks. These are often mined for both gold and copper. Composition and extraction. Gold ore contains varying amounts of gold, often measured in grams per ton, G/T. The gold may be free milling, meaning it can be extracted by simple gravity separation, or refractory, requiring complex processes such as roasting, pressure oxidation, or bioleaching to liberate the gold. Modern mining operations use techniques like cyanide leaching, where the ore is treated with a cyanide solution to dissolve the gold, which is then recovered through processes like electrowinning or activated carbon adsorption. Economic importance. Gold ore is a critical resource for industries and economies worldwide. Gold is not only valued for its beauty and rarity in jewelry but also for its applications in electronics, dentistry, and aerospace due to its excellent conductivity and resistance to corrosion. Environmental impact. The extraction of gold ore can have significant environmental impacts. Mining processes can lead to habitat destruction, water contamination from toxic chemicals, and air pollution. Responsible mining practices and stricter regulations are essential to minimize these effects. Understanding the geological characteristics of gold ore and the methods used to extract it is essential for efficient mining operations and the sustainable use of this valuable resource. Formation of gold ore. The formation of gold ore is a complex geological process that takes place over millions of years. Gold deposits are typically associated with specific geological events, such as volcanic activity, hydrothermal fluid movement, and tectonic processes. These processes concentrate gold from the Earth's crust into economically viable deposits. Below is an in-depth explanation of how gold ore forms, its various geological settings, and the mechanisms involved. Processes leading to gold ore formation. Gold in the Earth's crust is primarily derived from the primordial processes that formed the planet, as well as from subsequent geologic recycling. The formation of gold ore typically involves the following stages. 1. Magmatic and mantle processes. Gold originates deep within the Earth's mantle. During volcanic activity, magma rises toward the surface, carrying trace amounts of gold and other metals. These metals are dissolved in the magma and become concentrated in the upper crust through magmatic differentiation, where lighter materials rise and heavier materials sink. 2. Hydrothermal activity. Hydrothermal fluids, which are hot, mineral-rich liquids circulating within the Earth's crust, play a crucial role in the concentration of gold. These fluids are heated by magma chambers and travel through cracks and fractures in the rock. As they cool, they deposit gold and other minerals into the surrounding rock, forming vein deposits. Quartz veins are common carriers of gold in these systems, often visible as gold-bearing lodes in hard rock formations. 3. Metamorphism. During regional or contact metamorphism, where existing rock is transformed by heat and pressure, gold may be mobilized from the original host rock and concentrated into new locations. This process often produces gold deposits in metamorphic belts or areas near fault zones. 4. Sedimentary processes. Gold can also form through sedimentary processes. During erosion, gold-bearing rocks are weathered, and the liberated gold particles are transported by rivers and streams. This process creates placer deposits, where heavy gold particles settle in streambeds, alluvial fans, or beach sands due to their high density. 5. Biological and chemical interactions. Some studies suggest that microorganisms may play a role in the concentration of gold. Microbes can dissolve gold in solution, enabling it to precipitate in specific environments, creating nugget effects. Geological settings of gold or formation. Gold deposits form in various geological environments. Each setting involves specific processes and conditions. 1. Greenstone belts. Greenstone belts are ancient, tectonically active regions composed of volcanic and sedimentary rocks. These belts are rich in lode gold deposits, often formed by hydrothermal fluids that permeate through fractures. Example: the Witwatersrand Basin in South Africa, the largest known gold deposit. 2. Orogenic belts. Gold deposits in orogenic belts are often associated with mountain-building processes, orogeny. The compression and heating during tectonic activity generate hydrothermal fluids that concentrate gold. Example: the Mother Lode Belt in California, USA. 3. Epithermal systems. Near-surface hydrothermal systems associated with volcanic activity are common settings for epithermal gold deposits. These systems often produce gold along with silver. Example: gold deposits in the Andes Mountains, South America. 4. Carlin-type deposits. These unique deposits form in sedimentary rocks where gold occurs as microscopic particles disseminated in fine-grained rocks, such as limestone. Example: Carlin Trend in Nevada, USA. 5. Placer deposits. Placer deposits result from the erosion and transportation of gold from its primary source. These are found in riverbeds, floodplains, and beaches. Example: Klondike Gold Rush deposits in Yukon, Canada. Mechanisms of gold concentration. Several mechanisms are responsible for the concentration of gold during or formation. Pressure and temperature gradients. Changes in pressure and temperature during the cooling of hydrothermal fluids cause gold to precipitate out of solution. Chemical reactions. Gold often precipitates when hydrothermal fluids mix with cooler groundwater or encounter chemically reactive rocks, such as carbonates or sulfides. Boiling of hydrothermal fluids. In some cases, the sudden boiling of hydrothermal fluids causes gold and other minerals to precipitate rapidly. Gravity sorting. In placer deposits, gravity concentrates heavier gold particles in areas of slow water flow or natural traps, such as bends in rivers. Modern implications. Understanding the formation of gold ore is critical for modern exploration and mining industries. By studying the geological processes and structures that lead to gold concentration, geologists can better locate and assess potential gold deposits. Additionally, insights into these natural processes inform sustainable mining practices and guide the search for new, untapped sources of gold. Types of gold ore. Gold ore comes in various types, each formed under unique geological conditions and containing distinct mineral compositions. The classification of gold ore is based on its geological origin, mineral association, and the processes that concentrate the gold. Understanding the different types of gold ore is crucial for efficient mining and extraction techniques, as each type requires a tailored approach. Below is an in-depth exploration of the main types of gold ore. 1. Lode gold ore, vein deposits. Lode gold ore refers to gold that is embedded within veins or fissures in rocks. These deposits are typically associated with quartz veins and are one of the most common sources of gold. Formation. Lode deposits form when hydrothermal fluids carrying dissolved gold flow through fractures or faults in rocks. As the fluids cool and pressure decreases, the gold precipitates out of the solution, forming veins. Characteristics. Often associated with minerals like quartz, pyrite, arsenopyrite, and chalcopyrite. Gold may occur as visible grains or be microscopically disseminated within sulfide minerals. Examples. Mother Lode Belt in California, USA. Kalgoorlie Super Pit in Western Australia. 2. Placer gold ore. Placer deposits form through the mechanical concentration of gold, usually in riverbeds, streambeds, or beaches. This type of deposit results from the weathering and erosion of gold-bearing rocks. Formation. Gold-bearing rocks are weathered, and the liberated gold particles are transported by water. Due to its high density, gold settles in low-energy environments like bends in rivers, gravel bars, or along beaches. Characteristics. Gold is found in the form of nuggets, flakes, or fine particles. Often accompanied by heavy minerals like magnetite, ilmenite, or garnet, which also settle due to their density. Examples. Klondike region in Yukon, Canada. California gold rush sites. 3. Carlin-type gold ore. Carlin-type deposits are sedimentary hosted, low-grade gold deposits characterized by microscopic gold particles. These deposits are among the world's most economically significant sources of gold. Formation. Formed when hydrothermal fluids carrying gold interact with carbonate rocks like limestone. Acidic fluids dissolve the carbonate rock and deposit gold as fine particles in the pores or fractures. Characteristics. Gold is invisible to the naked eye and occurs as submicroscopic particles within host rocks. Typically associated with arsenic and antimony minerals like realgar and orpiment. Examples. Carlin Trend in Nevada, USA, which accounts for a significant portion of U.S. gold production. 4. Epithermal gold ore. Epithermal deposits form near the Earth's surface due to hydrothermal fluids derived from volcanic activity. These deposits often contain gold along with silver and other metals. Formation. Hydrothermal fluids circulate through fractures in volcanic rocks, depositing gold at shallow depths. The precipitation of gold is often triggered by boiling or chemical reactions between the fluids and host rocks. Characteristics. Found in association with minerals like quartz, calcite, and sulfides. Can contain high-grade pockets of gold alongside low-grade disseminated deposits. Examples. Gold deposits in the Andes Mountains, South America. Hishikari Gold Mine, Japan. 5. Porphyry gold ore. Porphyry deposits are large, low-grade deposits associated with porphyritic igneous rocks. These deposits are often mined for both gold and copper. Formation. Gold forms during the cooling and crystallization of magma. Hydrothermal fluids expelled from the cooling magma deposit gold in the surrounding rocks. These deposits are typically large but with low concentrations of gold. Characteristics. Disseminated gold occurs throughout the host rock, often with copper and molybdenum minerals. Economically significant despite low grade due to the large scale of the deposits. Examples. Graberg Mine in Indonesia. Bingham Canyon Mine in Utah, USA. 6. Refractory gold ore. Refractory gold ore refers to ore that requires complex processing to extract the gold due to its association with certain minerals. Formation. Gold is finely disseminated within sulfide minerals like pyrite and arsenopyrite or chemically bonded with other elements. This makes conventional extraction techniques like cyanidation ineffective. Characteristics. Gold is often locked within sulfides or coated with organic carbon, preventing simple leaching. Requires advanced techniques like roasting, pressure oxidation, or bioleaching. Examples. Certain deposits in Nevada, USA, and South Africa. 7. Oxidized gold ore. Oxidized gold ore forms when primary sulfide deposits are exposed to weathering and oxidation near the Earth's surface. Formation. As sulfide minerals oxidize, gold becomes liberated or concentrated in a porous, oxidized zone called a gossan. These ores are easier to process compared to refractory ores. Characteristics. Gold may occur as free-milling grains or in association with oxides of iron and manganese. Typically found near the surface above sulfide-rich deposits. Examples. Supergene-enriched gold deposits in South America. 8. Alluvial gold ore. Alluvial gold ore is a subset of placer deposits and refers specifically to gold that has been deposited by water flow in loose sediments. Formation. Similar to placer deposits but typically formed over larger areas with extensive sediment layers. Gold is carried downstream from its source and concentrated in floodplains, deltas, or lakes. Characteristics. Often found as fine particles or dust in sand and gravel. High purity due to natural abrasion during transport. Examples. Witwatersrand Basin, South Africa. 9. Sulfide-associated gold ore. Sulfide-associated gold ore contains gold locked within sulfide minerals such as pyrite, arsenopyrite, and chalcopyrite. Formation. Gold is deposited with sulfides during hydrothermal activity. This type of ore is often associated with volcanic and metamorphic rocks. Characteristics. Requires advanced techniques to liberate gold from the sulfides. Gold is often invisible to the naked eye. Examples. Gold deposits in the Barberton Greenstone Belt, South Africa. Summary. Each type of gold ore represents a unique geological setting and requires different mining and processing methods. From easily accessible placer and lode deposits to challenging refractory and sulfide-associated ores, understanding the characteristics of each type is essential for efficient gold production. Advances in exploration and extraction techniques continue to improve the economic viability of even low-grade and complex gold ores, ensuring the continued importance of this precious metal in industry and commerce.